I am very pleased to introduce the next speaker, Professor Derek Hoiem from the University of Urbana-Champaign in Illinois. Sorry for the pronunciation. Derek is also a co-founder at Reconstruct, and today he will share some findings that he has from both the company as well as his research in Illinois. Thank you, Derek. The floor is yours.
Okay, thanks a lot. Just to check, everybody can see my screen and everything, right?
Yes, all good.
Okay, cool. Thank you. I'm really happy to be here, and I'm really glad that this workshop is taking place. So as you said, I'm a professor at University of Illinois, also co-founder of Reconstruct. So I think a lot about computer vision, but especially lately in the context of construction, and wanted to share some of the thoughts I had as a result of my experiences in applying computer vision within a startup. So it's really easy to tell a good story about the potential for impact in construction and in the built environment in general. So for example, for US infrastructure, 77% of bridges are at least 40 years old. 1 out of 11 is structurally deficient. Of course, they're used millions of times a day. And there's 600,000 bridges that need to be inspected every year or two. But bridge inspection is expensive. You have to stop traffic. It can be dangerous. It's hard to get access to different parts of the bridge where you need to take photos. So in practice, these inspections are not done as often or as thoroughly as they should. And this can result in catastrophes like bridge collapses or failures at power plants and other things that you'll hear on the news. Likewise, in construction, there's a huge productivity gap, a different problem, but a big productivity gap between construction and manufacturing and basically every other industry. While all the other industries have improved in productivity greatly in the last 50 years, construction has been fairly stagnant. And it's not because construction was already super productive and everything was going well. It's very common in construction projects for projects to run over schedule and over budget. And that causes problems for all kinds of people. For the owner who needs to start making money on his investment so that he can start paying off his loans. For the general contractor who may start paying hefty fees if the project is too expensive or too slow. And for subcontractors who need a reliable schedule so that they can keep their whole crew employed continuously. A lot of these problems in construction come down to a problem of understanding what's going on everywhere on the site all the time and using that information to effectively coordinate the entire project, which is a really difficult task because you could have a few superintendents, a couple dozen subcontractors doing different trades, hundreds of workers on the site at any given time. And if one little piece of the, if one subcontractor is like a few days behind schedule, that can throw a wrench in the whole process, delay the entire project as a whole, and cost millions of dollars. And often the communication is done through like blueprints and notes on the blueprints. This is an actual example. And so you can see that communication may fall through the cracks. You may have failures in coordination. Dodge and Cox shows that 35% of costs in construction are due to failures in coordination. So we basically need to get more transparency for all stakeholders on the project and better coordination. So there's lots of needs in construction and AEC in general, and I could list many more. On the other hand, we have like amazing advances in computer vision. So we have the ability to detect objects, to segment objects much more accurately than we could even a few years ago. We can estimate pose and activities, which could be useful for safety applications. We can create 3D models of scenes from photographs. And so using these technologies, computer vision can provide that situational awareness that is needed to more effectively monitor or more effectively manage the construction projects, and also create an as-built digital twin that can be used for progress and quality monitoring, as well as for operations and maintenance after the construction is finished. So so far I've been talking about this at a level that is very familiar to anyone who does research. I've motivated the needs of an industry, these broad needs. We want to improve productivity, we want to improve safety, keep projects on time, reduce project costs, improve the quality of the build, identify defects earlier, and so on. And we have technologies that could plausibly help with these problems. And in research, often this is where we leave it. We can write a paragraph motivating our research, sounds plausible, people understand why we're doing the research, and that's good enough. But in practice, this leaves a big solution gap. So we recently held a AI in construction workshop where we had 175 professionals, mostly from construction companies and construction technology companies, to try to understand what are the real problems in construction and what is the potential in the near term and midterm for AI to help solve those problems. And one of the attendees, Brian Krause from Clark Construction, said, I saw one gap in connecting academia and industry. I felt like academia was looking for the next thing to research. You know, they publish a paper, they're satisfied with the solution, but in fact, it's not refined, targeted, or useful for construction. So this is what I call the solution gap. It's that we have a technology that works well enough for a paper within like confined experiments on an abstract problem. And we can see how that might address some kind of like broad need in the industry, but it doesn't actually solve a problem by itself. And so, what I want to talk about is how we can evolve from that kind of technological solution into a actual workflow solution. And that happens when you think about the jobs that people actually do in the field, the process that they go through, what parts of the process cause pain, in other words, like take a lot of time or cost a lot, and then where the technology can come in as part of that existing process to facilitate the workflow. So it's a little bit of a different way of thinking than we often think in purely academic research. So I'll give a couple of examples from Reconstruct. One is in inspection. So the prompt in inspection, you want to inspect like cooling towers, chimneys, bridges, other critical infrastructure. And often these structures have hard to reach areas. So you can take photos with drones, but then the inspector has to like annotate on top of the photos, then somehow map those annotations onto like organized drawings or 3D models in order to report to the owner where the structure has defects, you know, what would be the cost for repairs and so on. So from a technical perspective, basically we can just take the photos, create a 3D model, and then provide tools to inspect on the images and map those interactions and annotations onto a 3D model so that you have an organized set of defect locations. And so here's an example of that. This is kind of an earlier version of our system where a point cloud was created. In this case, it was from DSLR images on the ground. You can then select those photos or select a point on the model to find a photo of that scene. Then you see the photo in full resolution. You can zoom in. You can take measurements. You can identify defects and add pins on top of the photo. And then because there's a model in the background, all of this gets, anytime you interact with the photo, you're actually interacting with an underlying 3D surface. And so at the end of this, you get a set of measurements and defects with severity and so on that you can use to report. So that's like a good solution from a technical point of view, and you know, it's somewhat useful even in practice. But once we started working with customers, we realized that there are some parts of the inspection workflow that we hadn't fully considered. So the way that the inspection actually works is that somebody travels to the site. They might need to fly out there or drive a long way. They'll take photos using a drone or DSLR. They'll go back to their hotel or office somewhere where they have internet connection, upload the photos. They'll start the modeling process. It may take some hours for the modeling process to finish. Then once that's done, they or somebody else can use our viewer to annotate the defects. And then they have to take these annotations and they create a report for the owner that would show location and severity of defects as well as repair costs. So one area of this that we kind of underestimated at first is just that the beginning pain point. So the part about capturing the photos and then getting it into the system is a very time-consuming process. And it's really the travel to the site. So they're happy to take a lot of photos once they get there. They don't mind if they spend an extra hour on the site. But once they leave, if they go back to headquarters or whatever, and they don't want to find out much later that they need to travel back to the site and fly the drone again and get more photos. So it became really important to avoid having them repeat that process. And so there's a few ways that we address this. One is to provide clear guidelines for capture so that on their first visit, they get all the photos that they need. A second is that we did a lot of algorithmic improvements to maximize the completeness of the registration. So in a lot of research on structure from motion, it's based on internet data sets. It doesn't really matter if you register all the images because there's like thousands of images. They're just taken by random people who had no objective. And so if you drop a big percent of them, it doesn't matter because, as long as you get a complete model at the end without major misregistrations. But in inspection, all the photos matter. They need to see all parts of the surface, and so this completeness is a really essential part of the application. The third way that we address this is by creating fail-safes. So if by creating like multiple reconstructions in case one complete reconstruction wasn't possible and having tools to register them, and being able to approximately register the images using the drone sensor orientation and positioning data. So one thing about when you apply something, often you can't just say it fails or it succeeds. So like average success rate isn't really a thing. Really the question is, how long does it take somebody on average, or what's like the range of times that it takes somebody to complete the whole process? And if your algorithm fails, then that means that somebody has to do some kind of workaround. So the question is like, how involved is that workaround? The other like glaring gap in our solution, as I described it before, is that we didn't have any reporting mechanism. So we didn't have any way to get those annotations out of the system. So with our first big customer, they said, okay, well, you need to make an Excel export like right away. So we did that so we could export those annotations with links to the original images as documentation. And then we created a couple of more tools that are really nice for this. So one of them is that we can take those photos that are aligned to the 3D surface that we've created, and from them and the surface, create an unwrapped surface. So whether it's a chimney, which is a kind of conical shape, or a cooling tower, which is parabolic, or like a flat surface, we can create a high resolution map using all of the original images. And then we can map the defects that were annotated onto that surface. So we can create like a PDF document that has pages that correspond to different sections of the model. And then there's like PDF annotations on top of those pages that show where the defects were annotated. And so this made the reporting job much easier. Another thing we did, this was for MLIT in Japan, the Ministry of Land Information and Tourism. They already had some reporting format that they use for inspection. So we created the ability to create these reports from within our system. The inspector can create a custom viewpoint, an orthographic view from a certain perspective, and then they can annotate the defects within that existing report format and then export it and use it directly. So once we created this complete workflow, then our inspection customers were over the moon. So they said, you know, we're able to take that, map all of our defects, paste directly into a report. It was taking us days to do that portion of the report, and now it takes minutes. That was from structural. And in MLIT as well, you know, they really raved about how now they can take these like 2D orthographic views and create these reports very simply. And the key to this is that the technical solution was great. It's an essential part of the problem, but it's really only when you complete the end-to-end workflow that you create something that's extremely valuable for somebody. The second example is in progress and quality monitoring. So this is a much more complicated problem. It's actually like a set of problems. But here the problem is that you, at the start of a construction project and during it, you've got all these plans. You've got drawings, different kinds of drawings. You've got building information models, which are CAD models that have like 3D elements. You've got schedules, master schedules, weekly work plans. And the problem of progress monitoring is to see what's actually been constructed, how many elements or what length of elements and so on, and how that corresponds to the plan, to the schedules, like the weekly work plan or the master schedule. The problem of quality monitoring is to take what's been constructed and compare it to specs. In some cases, that could be like flatness or some kind of physical requirement. In some cases, it's just that that things are placed in the right position, like you put a hole for a duct in the place where the duct actually needs to go. So from a technical perspective, this basically means that we can create a 3D model from photographs. You could also use a laser scan, but that takes a lot of time. Overlay it on a BIM, and then you can compare what is there versus what should be there, or like compare it to the schedule. So again, like this is the workflow for quality monitoring. You take photos of the job site. Now, in this case, you need to take them on like a daily or weekly basis because, you know, the site is changing frequently. So, you know, if there's pipes put up on the interior of a wall, then you need to take photos of those pipes before the wall gets covered up with gypsum board. And then, you know, when you take the photos, you have to return to a Wi-Fi zone because there might not be Wi-Fi on the site. Upload, again, start the modeling process. You can't do anything until that finishes. Then use the viewer. You can do BIM overlay inspection. We create lots and lots of tools for doing different kinds of progress and quality monitoring. And then you can communicate issues to the team in your weekly pool planning meeting or to subs architects and other stakeholders by like messaging screenshots and stuff like that. So, so there's actually like different pieces of this workflow that I could pick on as us not initially satisfying well enough. But again, I want to focus on this early part, which was the problem of getting the data into the system. So in research, we always assume, we pretty much always start with a collection of images that just was magically given to us. Yushin was showing, like explaining how the organizers created these amazing benchmarks. And in that explanation, he made clear, like, it's actually a lot of work to get this data and to organize it in a way that makes it useful. And in practice, that's a big problem because you're relying on your customer or somebody on the job site has to collect that data. That's expensive and it takes time. And so this is a cost to your solution. And so really minimizing that data collection effort is an essential part to making computer vision effective on construction sites and in many other applications. So, so one of the issues is that it's time consuming. And if you're using a drone, it's logistically complicated to take the photos. You have to watch out for the crane. You might not be able to fly the drone in a city. Certainly can't fly indoors. Another problem is that it can be time consuming to upload. Sites, you know, even the main office might not have a very good internet connection. And videos can be huge and take a lot of time. And then the other problem is that there's a lot of touch points here. So you have to take the photos, go back somewhere, upload, then start the processing, then wait, then you can do stuff. And so all these touch points with time in between reduce the effectiveness of the solution. So we created a variety of improvements to address these. One is that we enabled automatic capture by crane mounted cameras. Another company, Sincera, had these cameras that you could mount on cranes. We made it so that our system could automatically pull the images from the sensor or from the images created by the sensor so that as the crane moves around, we get photos of different parts of the scene, then we can create automatic reconstructions every day. Another is that we made capture easier on the ground or indoors using 360 video. Somebody can just walk around with a consumer 360 camera. And that required that we create new reconstruction algorithms that are robust for reconstruction from 360 videos in these challenging indoor environments where you have like textureless surfaces, reflective surfaces, thin structures, and so on. Another is that we reduced the upload speed by reducing the frame rate of the videos, which sounds simple, but then we had to make much more robust registration and reconstruction algorithms that can work just as effectively with fewer images. And then finally, we made a no-touch upload processing alignment process. So somebody just after they do the capture, it uploads, it figures out what it can align to. It does the reconstruction, it does the alignment, it gives people back the registered photos within minutes, and then gives them back a reconstructed model within a few hours. And that required lots of different improvements as well, including like automated alignment of captures to drawings, which have no like manual annotations on them. So here's an example of our system. In this case, it's for a renovation project. Somebody has taken a video by 360 camera, walking around for a few minutes. We can create these 3D models, maps. You can do a like photo tour. So you can inspect the site that way. You can see in the bottom left that you can always see where you are in reference to the drawing. You can also perform measurements either over the images or over the drawing because all of this data has like an underlying 3D structure, even when it's not shown. And you can flag issues. This also ties into like a phone app where somebody can report progress or report like issues that they identify on the ground and take snapshots of them. And so we provide like this, complete workflow that integrates the existing plan documents as well as schedule with the reality. So there's one more example. Some more example is shown by, and this is in the words of a customer. In another case, this is a owner representative. So they represent the owner to make sure the project is done well.
Using Reconstruct on this project as part of our owner reviews, our reports have come to life. We bring the construction site to the decision makers and we can walk them through the sites with the photo captures. We can show them where things are, where activities should be. We tie it all into the schedule. We then overlay the BIMs and we use this process to validate what was installed to what was actually modeled, and it's a game changer. Those meetings, what took us 3 weeks to compile that P6 report of 1,600 pages, we're now down to 1 week of working with Reconstruct and in our meeting with the owner where all stakeholders get all of their questions answered at one shot.
So in general, in application of construction, of computer vision to construction, and in many other areas, there's kind of like 3 main parts to the workflow. So one part is that you have to capture the data and get it into the system. Another part is that once you have the images, then you process it. You do your recognition or reconstruction. So you're producing like image level or image set level predictions. And then the third part is that you have to get actionable intelligence out. Like nobody cares how many bounding boxes you have in your scene. They might want to know, where the sprinkler's installed in the right location. And in the research, we often just focus on the center box, the processing. We're given the data. We do like the kind of low-level processing in terms of it's not actually useful yet. And then we assume that somebody else will take care of turning that into useful information. But when you think about the whole workflow, then you realize that there's a lot of other problems that are not currently being addressed that we should be addressing. So one of them is just the capture process, finding any way to simplify the capture, meaning taking photos and getting them into the system. It could be automated, like with the crane photos that I mentioned, or just having a robot that can navigate the environment, which is very difficult for indoor construction scenes, and take photos where they're needed. Another problem on the process side is creating more robust algorithms for 3D reconstruction and recognition that can produce good results in complex environments from a few photos. So it's really the complex environments that's a big challenge in construction, and also minimizing the amount of capture that you need to do to get good results. And then the other is evaluation. So I really liked that the organizers spent a lot of time thinking about how you should evaluate their challenge. We need evaluations that that are meaningful for the application, and also that support guidelines for when or where a method works. So telling me that something works like 90% of the time over some data set isn't that helpful. What I really need to know is, when can I use it and when can I not use it? What kind of information do I need to give the system in order to ensure that it works? And then given that it needs to work, or there needs to be a good workaround in the case of a rare failure. And then the third part is getting that actionable intelligence out. And really the key there is being able to integrate the visual analysis with scheduled drawings and other documents, so other kinds of structured information, because it's really the combination of the visual information that we can extract with the other kinds of information that already exist about a building or a project where you can actually create value. So the key takeaways is that computer vision has the opportunity to make a huge impact on the built environment. I showed a couple of examples. In order to do so, though, we need to think beyond the technical solutions and think more about complete workflow solutions. And especially, I think, as researchers, what we need to think more about is how you get the data in and how the analysis gets out. And when you think about it that way, it reveals new hard research problems like data integration, alignment, robust analysis, and methods for automated reporting. Thanks very much, and I'm happy to answer any questions.
Thank you very much, Derek. To all attendees, you can either ask your questions in the Q&A box. You can also raise your hand and we'll give you access to speak. In the meantime, while we're waiting for more questions to come in, there is one for you, Derek. What kind of 3D modeling techniques are used to ensure enough reconstruction quality for inspection? Is a standard toolbox like Hoiem good enough?
We didn't find that there's any available solution that's quite good enough. So that's something that we've spent a lot of time on in the last few years. Hoiem is it's a pretty good solution for both MVS and SFM. And there's problems with the speed as well as completeness. So we found, I can't talk about, unfortunately, I can't like kind of reveal the secret sauce. But we found that incorporating elements of like global SFM as well as incremental SFM was important because they both have their own advantages. And we also just have, over time, made a lot of improvements to every part of the process, from matching to finding match candidates to doing like reconstruction and clustering and basically kind of grinding on all the different parts of the pipeline.
Great. We have more questions coming in. Let's see how much time we have to go through them. Michael Helmenberger, apologies again for the pronunciation. What are the accuracy requirements for your customers?
So that's a very, okay, so there's many ways I could answer that. So the one way is in terms of the precision of the point clouds. We say that we're accurate within like 1/2 inch or 1 inch. So this can be used for, in terms of quality monitoring, you can say like whether something was put in the right position, but it's not really useful for like the kind of flatness quality checking that you would do, that you would really need a laser scan or other methods for. And in terms of like the accuracy, in terms of like whether the model is complete or you have holes in it, things like that, it kind of depends on the application. So I guess what I would say though is that for the purposes of progress and quality monitoring and for inspection, like our current method is already sufficiently accurate. There's cases where for bridge inspection in Japan, they'll have a drone fly like 1 foot away from the bridge by like having some like basically touching the bridge and running up it. That can take photos of such high resolution that we can detect defects that are sub-millimeter. So really the accuracy that you get is a matter of how you capture the data. And I think generally there's not an expectation of the same level of precision that you would get from laser scans, but but the speed of a visual capture tends to outweigh the disadvantage of having a little bit coarser geometric information.
Thank you, Derek. We have someone asking, are you using only high-end equipment, for example, DSLR cameras, or did you try using mobile camera or other lower SNR cameras?
Yeah, that's a good question. So we don't use any, we don't take the pictures ourselves. So our customers do. And we recommend things to them. The most common solution, especially for interior capture and even for some of exterior capture, is just to use consumer 360 cameras, like the X2, the Insta360 cameras. So they're only like $400 cameras. So that's what we're doing most of the reconstruction from. But in the case of drones, people will usually get a decent drone and camera that will be like a couple $1,000s, like an Inspire or something like that. But we're not using typically any very expensive or highly specialized equipment.
And I'll ask one last question, although we have many more. Have you used LiDAR data in combination with image data? What challenges, research and practical, do you see in this combination?
So we have the ability to import the LiDAR data into our system, but we haven't really used them in conjunction. So somebody can view their like point cloud from images at the same time as like combined with the LiDAR scan, but we haven't done any joint analysis. I think that generally images have more information than laser scans, although for some tasks it's not as convenient to extract that information because they tend to have much higher resolution than even the laser scan. So I think there are a lot of good problems for combining that information, but I can't really speak from practice about like what are the big challenges.
Okay, sounds good. I think we should, as I said, we have many more questions, but I think we should conclude it here. Thank you so much, Derek, for the wonderful presentation.